new Stein's also is coming from Moscow State, and we'll talk about nonlinear PDEs, Schottky problem, Jacobian conjecture, commuting differential operators.
Thank you very much. Let's consider two differential operators of order n and differential operator of order m. And let's consider the commutativity condition of these operators. So the commutativity condition is equivalent to a complicated system of nonlinear differential equations, and sometimes it is very important to know how to find coefficients of commuting operators explicitly. So later I will tell why it is important. And there is a theorem of Bushnell and
I didn't hear what he said.
why is it important to know how to find coefficients of commuting operators explicitly?
So coefficients of what?
Of commuting operators. So you have
Commuting operators.
yes. So you have a differential equation, nonlinear differential equation. You want to solve this differential equation. You want to know how to solve this equation. The same is how to find coefficient. So there is a theorem of Bushnell and Chauncey proved in 1915. They proved that if two differential operators commute, then there is a non-zero polynomial R of Z omega such that R of Ln, Lm equals 0. So the curve defined by this polynomial is called spectral curve. So
why can't you take ZW minus WZ?
it's just
Because that's automatically zero.
Yeah, because it's a polynomial.
yes,
These are commuting variables.
Okay.
yes. This is a total. So non-zero polynomial. No, I mean this. No, I mean this. No, many people ask. No, many people ask the same question because they commute this Z and omega, and so now let's consider this system of differential equations. So and it appears that this system has solution if and only if the point Z omega is a point of our Riemann surface. And it appears that for almost all points of our Riemann surface, the dimension of solutions of the system is the same. So here we have linear differential equation, here we have linear differential equation. And for almost all points, the dimension of solutions of the system is the same. And the dimension of solutions of this system is called the rank. So again, just for almost all points, the dimension is the same, and this dimension is called the rank. Almost all points. Yes, almost all points. We have a Riemann surface defined by this polynomial. For almost all points of our Riemann surface, the dimension of solution of the system is the same. Now let's consider our function not as a function only of x, but no, it's all complex. X is a complex too.
But why is it a Riemann surface?
Okay, it's not a curve. Just you can imagine.
So it could be singular.
It can be singular. I can say more that any Riemann surface or any curve, any singular or non-singular, can be a spectral curve of two commuting operators. So
The
dimension jump have anything to do with the singularities?
If your spectral curve is not singular, then you can say that for all points the dimension is the same. The problem is when your spectral curve has singularities. And let's consider our common eigenfunction. When I say common eigenfunction, I mean the solution of this system as a function, not only a function of x, but also you can consider it as a function on our curve. Yes, and it appears that as a function on our curve, it's a Baker-Hazer function. So let me tell you briefly the definition of Baker-Hazer function. So let's take.
Can you write down the name?
Yes, I can. I can.
Oh, Baker.
No, it's. I can. Now, for me, it's not easy to. I'm not sure that. I think it's.
What's the math?
What is this? Like this? Okay. So let's take a Riemann surface of arbitrary genus, and let's take a fixed arbitrary point Q, and let's take a non-special divisor of order G, gamma 1, gamma G, and let's consider the function which, and we call function a Baker-Hazer function if it has essential singularity at this point, at point Q. And simple points at this point, or simple poles at this point, points gamma 1, gamma G. So if we take, so for arbitrary Riemann surface of genus G and arbitrary fixed points at non-special divisor, such function as exists and it's unique. So it has essential singularity at point. So that's all. So I don't want to say some about technical details, but I want just to have a function which has an essential singularity at point Q and has simple poles at points gamma 1, gamma G. And that's all.
So you're saying that these guys are
yes,
okay.
yes. So the
solution, these eigenfunctions, the solutions of this system of differential equations.
you can see it because if you consider like differential equation in simple form, you will have exponential function, the common eigenfunctions. Yeah, and this is some modification of this simple case. So that's why we have a essential singularity. Yes. Now such function exists and it's unique. So we can do we take a Riemann surface, take this point, and for G points, non-special divisor, and this function exists and unique. Now we can do the following. We can take just this function. We can forget about commuting operators. We can take this function, and then it's not difficult to show that if we know common eigenfunctions, then we can construct commuting operators using Baker-Hazer function. And I want to say that Baker-Hazer function can be found in terms of Riemann theta function. So there is.
So you said it's unique, but for example, if the genus is 0, that's not true.
You don't think it's unique?
Why? So you have just a sphere. You take a point.
You're saying that
and you don't have
an essential singularity is unique.
No, but you don't have a pole. So you need a function which has an essential singularity at this point, and that's all. Only essential singularity.
But the exponential and e to the z squared.
He means prescribed type, essential singularity of prescribed type. Mimics n and m.
Okay.
Of that type is unique. Of that type.
Okay.
That's what he means.
What's the answer?
The answer is that it's not just an essential singularity, but it's a type of essential singularity.
Yes. Yes. Yes.
N and M. Okay. Exponential.
Well, he's saying no matter what, if If you have some prescription of the essential singularity and simple poles of these other things, then the function is unique.
Yeah, so I told you before that I want to say some technical, it's some technical thing, but the idea is the function has essential singularity at some point. There is an explicit formula for Baker-Heiser function in terms of Riemann theta function, and so if we can find such function, well, then it's not difficult to show that we can construct commuting operators. So we can find coefficients of commuting operators explicitly in terms of Riemann theta function. So there is an explicit way of finding coefficients of commuting operators. Now let's consider an example. Let's consider of differential operator of order 2 and differential operator of order 3. So I don't want to write which kind of operators I'm considering. Just now it's not important. So let's consider the commutativity condition of the following operators. I like this. So you can tell me that here we consider differential operators of many variables. Yes, but I told you before we're considering operators of one variable. So I don't say that all previous technique can be used for operators of many variables. I wanted to say that these operators, these two operators, they depends on variable y and t in a simple way, and that's why we can just a little develop previous technique for using for finding coefficients of commuting operators in the following form. So we just develop a little this technique of Baker-Heiser function for finding coefficients of the following operators.
So now you're describing the new work or the new work?
No, I think it's old work. It's like 1970s, 75. So this is about this series sounds like 1917, 1918, some 75 maybe.
Some kind of heat flow associated to these operators?
Sorry?
It's some kind of heat equation?
No, it's a KP equation. So if you write the separators, you will get the following equation. This equation is called KP equation. It has the following form. So, as I told you before, we can find the coefficients of the separators explicitly in terms of Riemann theta function. So it means that we can find coefficients, solutions of this system in terms of Riemann theta function. So this solution will have the following form. It's like 2. So U, V, and W is G-dimensional vectors. They are not arbitrary. There are some vectors. So I don't want to say which kind of vectors are they, but I wanted to say that they are not arbitrary. Also, Z0 is just, you can think it is just an arbitrary number. Also, we should say that theta function depends on symmetric matrices with definite, with negative definite real part. Yes, and and I told you before that when we construct Baker-Heiser function, we take Riemann surface. Yes, but and we construct this theta function using the Riemann matrix of the Riemann surface. So it is a Riemann matrix. It's a matrix of periods of holomorphic differentials. So we know that the dimension of Riemann surfaces of G naught G is equal to 3G minus 3. Yeah, but the dimension of symmetric matrices is equal to G multiplied by G plus 1 divided by 2. So you see that if G greater than 3, then not all symmetric matrices are matrices of periods of holomorphic differentials. So it means that so there is a Schottky problem, Schottky problem, which the task is the following: like how to recognize Riemann matrices amongst all symmetric matrices. So there is a and you can ask me what will happen if I construct if I write the same formula, but write here not B as a Riemann matrix, right? Any symmetric matrix. So the answer is that there is a Novikov's conjecture. This now this conjecture is proved by Schroeder. So this conjecture tells us that this function is a solution of KP equation if and only if matrix B is a Riemann matrix. So ideally, you have a method how to recognize Riemann matrices amongst symmetric matrices, because you can just put your formula here and get algebraic equation on coefficients. But in fact, it's not so easy. But this conjecture is true. So this function is a solution if and only if this function, if and only if matrix B is a matrix of holomorphic, is a period of holomorphic differentials. So in some, you can say that this, in some way, this conjecture solves the Schottky problem. In fact, now, as I told you that
all Riemann surfaces as spectral curves.
yes, even if it's singular, so you can't use the same technique when your Riemann surface is singular, because you need to modify it. So because we say about set of functions, so on, but this is true, any Riemann surface. So
So this L2 and L3 these are some particular operators?
no, yes, there are some operators. So L2 has the following form. Yes, and the L3 it's like plus something, maybe like I don't remember, plus some other function. So in fact, you can consider such operators without loss of generality. You can, okay, I don't want to say, but you just need to take such operators. And
Just to one.
I have 3 minutes. Yes. So in this case, when you can find your coefficients explicit in terms of Riemann theta function, is the case when rank of your operators is equal to 1. So your rank is a common divisor of commuting. Is a common divisor of orders of operators, and that's why if you have, like in that case, if you have operators of orders and the orders are relatively prime, then you have operators of rank 1. So when you have your commuting operators is operators of rank greater than 1, then this case is much more difficult. So there is a classification of commuting operators in the same way, like you take Riemann surface and some additional data, but this classification was obtained by Kirchhoff, but in fact that classification becomes something like a theorem of existence when this classification just says you what kind of information you need to fix for constructing operators, but it doesn't give you effective method for constructing operators, like in rank 1. So I have 2 minutes, yes. 1? Okay, 2 minutes. Okay, one more thing about, I promised to say something about Jacobian conjecture. So there is an nth Weyl algebra. You can think about nth Weyl algebra as a differential operators of n variables with polynomial coefficients. So, and we say that homomorphism of Weyl algebra is an endomorphism if And there is Diximia conjecture, which says that any endomorphism is isomorphism. So let Dn be the Diximia conjecture for n well algebra. So Kontsevich, Cannell, below, they proved that if Diximia conjecture for nth well algebra is true, then Jacobian conjecture is true. Then Diximia conjecture for n well algebra implies Jacobian conjecture for n-dimensional Jacobian conjecture. And 2n-dimensional Jacobian conjecture implies n-dimensional Diximia conjecture. So if you prove 2-dimensional Diximia conjecture, you prove 2-dimensional Jacobian conjecture. So as I told you before, in this case it's important to understand how commuting differential operators with polynomial coefficients looks and to find them explicitly, because if you know a lot about commuting differential operators, so then you can say a lot about the endomorphism and you can say something about these. So I think that's all. Sorry?
You said Jacobian conjecture?
Yeah.
That's the one about the mappings from C.
Yes, about polynomial mapping from C and.
Not supposed to work on that.
Now, he just proved that you're not supposed to work on the Diximia conjecture.
Oh. It's too attractive, that question.
Okay. Any other question?